So far, we have done two examples related to the column subjected to moment in both axes. We did one for the short column, another one for braced and slender column. Now we're going to do another one, which is unbraced and slender column. The purpose is to demonstrate the calculation steps for the design of column subjected to moment in both axes under different circumstances. We're going to deal with the same column having the same specifications and details, just that the type of column differs. Since in our previous example, we found that in the design of the slender and braced column, the maximum bar area has been exceeded. That means the proposed size 150 times 300, it will be insufficient for a slender column. Knowing the maximum bar area has been exceeded, that means there is no point to proceed with the biaxial bending chart, which is this one. And the proposed section needs to be enlarged. Therefore, for this example, when we deal with the slender column and unbraced, the width of the section increases. This time we use 175 times 300. The other details and specifications will be the same. Without further ado, let us get started. We start with designing the nominal cover based on the equations given. It announced the nominal cover equals to 35 mm. Next, we need to determine the MED. Dealing with the slender and unbraced column, the MED is determined by this stress diagram as given in the equation here. You will need the first order moment plus the second order moment in order to determine the design moment. Let us first deal with the first order moment. Based on the moment given, you have moment in the major axis and moment in the minor axis. The bigger moment of the major axis, it will be 26.6. This will be used to compute M02, whereas the smaller moment will give you M01. It will do the same for the minor axis. To calculate the MED, you will need to deal with both axes, since the moment is acting in both axes. This M01 and M02 will have to incorporate moment due to the imperfection. The equations for the imperfections is MED times EI, where the EI is calculated by the effective length per 400. The effective length is given in the question. Major axis and the minor axis, two different values. Divided by 400, you get 2 EI, one in the major axis, another in the minor axis. And then calculate the M due to imperfections by multiplying EI with the NED. NED is 147.36 kN. You get moment due to imperfections 1.8 and 1.6 for the major and the minor axis respectively. If you look at the equations for the MED, the M0A is not required. Although it is given here, it is okay if you do not calculate this. Next, we need to determine the Eng-aim. The minimum moment is determined by E0, which is calculated as h per 30. And this h per 30 needs to be at least greater than 20. For the major axis, the h it will be 300. As for the minor axis, the h is 175. 300 divided by 30, you get 10 mm. 175 divided by 30, you get 5.8 nm. None of them are greater than 20. Then you will use E0 equals to 20. Eng-aim is calculated by multiplying the absolutes with E0. Absolutes 147.36. E0 equals to 20. You get MED equals to 2.95 kN meter. Next, you need to calculate the M2, which is the second order moment. There will be a series of equations. Most of the equations can be obtained, except KR. Since the first round of the calculations, we do not have the amount of reinforcement bar in the column. Therefore, we will start with assuming KR equals to 1.0. The rest of the calculation step, it will be the same as the previous example, which you need to first determine the FYD. 0.87 times 500, you get 435. And then you get the design yield strength. Using the FYD, which is 435, divided by modulus or elasticity of the steel, which is 200 gigapascal. You get epsilon YD equals to 0.218. Then you need to calculate the ratio 1 per R0. Here you will need the effective depth. This will be the effective depth, which you need to get the column dimensions minus the concrete cover minus the shelling minus half of the bar size. You need the effective depth in the major and in the minor axis. That means you need to get another effective depth here. The concrete cover is 35. The size of the shelling, it will be 6 mm, and the size of the main bar, it will be 20 mm. For the major axis, the H, it will be 300. 300 minus 35 minus 6 minus 0.5 times 20 mm. You get 249 mm. You will do the same for the minor axis, where your H now, it will be 175. Having two effective depth of 10, substitute into the equations, you get 2 ratio of 1 per R0. Next, you need to get the effective creep ratio. These two items here with the assumed number of 2.3 and 0.67. Multiply them, you get the creep ratio equals to 1.541. You need the beta for you to calculate the creep factor. The beta is given by this formula. FCK is 30 and the slenderness ratio is given in the question. You have slenderness ratio for the major axis and the minor axis. As a result, you will have 2 beta. Substitute beta and also the creep ratio into the equations. The creep factors are obtained as 1.2 and 1.0 for the major and the minor axis respectively. Make sure this creep ratio needs to be at least 1.0. The KR here is assumed as 1.0, since for the time being we do not have the AS. We will assume the KR first, later verify again once we have calculated the AS in the column. Next is for us to get the curvature 1 per R ratio, which is calculated from the curvature times the creep ratio times the KR. That gives you this value. You will do the same for the minor axis. 1 per R0 times the creep ratio times the Kr. Having two curvature here, you're going to calculate 2 E2 and equivalent eccentricity for the second order moment. This is the formula for E2. 1 per r0 is this. The constant C is taken as 10 as given in Eurocode, and then you need the effective length. The effective length for the major and the minor axis varies. Use the right effective length for you to calculate E2. Having the E2 calculated, multiply with 147.36 NED, you get the M2. You have one M2 for the major axis, another for the minor axis, and then you're going to apply them into the equations for the slender and unbraced column. From the equation here, you need to get M02, which are this value, one for the major, another for the minor, plus M2, one for the major, another for the minor, and then this whole thing here will need to be checked against the minimum moment. The minimum moment is only 2.95. This leads to you the MED is calculated on the basis of M02 plus M2, the summations of the first order moment and the second order moment. Up to this step, the calculations process, it will be similar to what we have done in our previous example related to the slender and braced column. The only difference it will be the equations used to determine the MED, governed by the type of the slender column. Once we have the MED, you will need to determine whether the effects of the biaxial bending needs to be considered. There are two possible outcomes. First, the biaxial bending may be ignored. If that is the case, you will need to design the major and the minor axis separately based on the MED obtained. Apply into the design chart and work out the amount of reinforcement bar required. Based on the required AS for both axes, you have to work out a common layout of reinforcement in the sense that the total amount of reinforcement bar will be sufficient both in the major axis as well as in the minor axis. The second possible outcome, it will be the biaxial bending cannot be ignored. In this case, you will need to determine which axis it would be more critical, and the MED on the more critical side shall be modified. These modifications will have to take into the considerations of the effects due to the MED of the non-critical axis. We shall discuss about this in the following videos.